looked like they were okay. But what I was going to tell everybody, I'm sort of with the homework. If you're 75% of the homework, I would kind of consider that good. So if you get to chapter 12 and it looks like you hate it, do half the problems or something, and then certainly on chapter 13, I'm going to go over it today too. I'm going to do half of each of those 2 chapters because I thought there was something in both of them that I wanted to know. Don't do the last problem of chapter 13 because I'm not going to cover that. So all chapter 13 has is one little old problem in it then, and it can literally be done in 5 seconds. So at least everybody do chapter 13 homework because it's like you divide 2 numbers and you're done. But yeah, if you're like I said, if you're 75% on the homework, I consider that you got there. So if you get there and you're getting a hard time on, like I say, if you're dealing with a set, there's 3 problems and one of them's just killing you, just turn 2 of them in and say, okay, I tried.
For every chapter then?
For every chapter. That's 2/3. That's 66%. Then I'll say, I'm trying. I try to see people trying and learning, and this kind of stuff. The good thing about the homework is it lets you try things once. So again, I want you. I've thrown a lot of the Excels up there that you can download, you can have, and I just want you to be comfortable with using this when the time comes. Yeah, because I think. Like today, we'll do chapter 12, and then chapter 13 we've got regression. And I honestly think that is one of the most useful little things for you to do. Because we think of linear regression, you've probably heard of that all the time. Fit a line to some data. Well, it doesn't have to be a line. It can be x squared, x times y, those kind of things, or x1 times x2. And so, to me, and again, this is built right into Excel. So it's like, hey, you type the data in, you select regression, you understand what it's doing so you don't goof it up, but hey, you got a tool now where you can fit a curve, fit any kind of goofy curve you want, and I think that's pretty darn useful, and it doesn't take, even if you, as long as you understand what it's doing, kind of like, gosh, I can remember the regression tools under data analysis, or you can use my Excel spreadsheet and just review it, and so. So these are kind of, I want you to internalize these tools because I do think you'll use them. And you'll be, God, I remember that, and I couldn't derive this because we didn't learn that. but I don't care. I can use this tool. I can get my data fit. I can go on and present it, and that's, to me, that's really what I want you to get out of here. So today we're going to do chi-squared. That's what that little symbol is. So proportion. So it's the analysis where we instead of having numerical data, we've got categorical data, we've got proportions. And so I'm going to do half the view graphs out of chapter 12. And remember, these kind of tests, they only tell you, if you got 3 or 4 different proportions, it's just going to tell you that there's a difference in them. It doesn't say which one, and then they've got that comparison procedure where you do the pairwise comparison and pick which one or ones are truly different. So same type of thing we've been doing in the past. When we've got a table of data and we're just asking ourselves, is there a difference between these data sets? So that's your goal on chapter 12. And then chapter 13 is the regression. And this is basically where we're just going to fit, data to a model. Okay, and I'll do about half the view graphs out of that. Now, I posted the whole set, so if you do want to go through them and look at them, that's fine. These view graphs are pretty good. They're generally well done and self-explanatory. So if you wanted to go deeper into the chapter, that's fine. And then the regression. In each of these, chapter 12, I've got an example that I do. I work the problem that's in the view graphs. So you've got a good Excel that shows you how to use that. And then chapter 13, I made up a regression to do, and it's got 4 different cases, and I'll discuss them with you because they illustrate how you can use it to go beyond just linear regression, which, that's important. Things aren't all linear. It's nice to be able to do x squared or x cubed or some other combination. And also, one of the sheets in the Excel, I purposefully make a mistake. And I want you to look at it so you don't make that type of mistake. And I'll leave it in there so you can see, hey, this is a pitfall, don't do this. And you can understand it. So, because that's one of the problems sometimes with things that are just tools built in. You can easily goof up if you don't know what you're doing. So that's where we're headed today. But, And you know, you guys should feel good. This is further than I've got in this class than any other class. And so y'all moved along well. But I think it's important because I feel like when I look at the book, this is the point you need to get to be able to, you know, because you think about it, we've done numerical, categorical, we've done how to plot them and make confidence intervals, we've done how to make inferential decisions on whether there's a difference, and then we've also got ANOVA, which is a real critical tool, and then regression, which I think is something that you can use just analyzing and looking at data. So, you know, a set of good statistical tools that I think you'll use. Yeah, so let's do these two half chapters anyway, and we'll see what we feel like. And let's see.
Have we seen our stuff?
Could be.
Last day of class.
I think there might be mice.
Oh, I just found a whole bag of them.
What'd you punch?
A whole bunch of them.
They're outside.
That was good.
No, they were not on the street. Not the
Parking lot.
Hey, did everybody have a good Thanksgiving, by the way? Yeah. Me too.
No, I brought a ton of batteries for me stuff, and I hid it in a drawer, and the drawer was like full of a bag of like 1,000 batteries.
Would you like a mint?
Yeah, I'll take a minute, then I'll flop around my mouth. You know.
What you need is some light.
Yeah, I made the mistake of trying to do a little plumbing over the Thanksgiving holiday. You know, I hate plumbing because it's not like, you know, you can put it all together right, it still leaks. You know, water goes through little holes. And I wanted to. You see little things, you know, the switch in my bathroom messed up. You can touch it, it doesn't come on. So I said, this is bad. I told my wife, no, don't touch it, let me fix it. So I fixed that, I'm feeling successful. I'll try to fix this little faucet that's dripping. And in the past, I just put the washer, you know, it's probably the third time, 30-year-old faucet, and I replaced the washer. Forget it, the faucet's ugly. I'll put a new faucet in. That was my mistake. You know, trying to get in there, trying to get the hole in the sink was just a little bit drilled poorly, so it kept leaking. So I kept working on that. So it took me, you know, 2 or 3 nights. I'd have to go back to Home Depot the next day, that sort of thing. And, you know, in the meantime, my wife and daughter pile all their junk in the sink. They're, you know, they're not happy with it, can't do their hair and stuff. And so it's really funny. And so Tuesday, by Tuesday, I got all that done. I was coming home from work Tuesday thinking, at least I don't have to do any plumbing tonight. I was sitting there having dinner, and my daughter's, hey, Dad, the kitchen sink's draining real slow. She's coming to me, she says, oh, it always does that. And I looked, well, you know, not that slow. So it clogged up. So, you know, I was like, okay, this is great. I jinxed myself by coming home saying I didn't have to do any plumbing. So I spent a night on that too. So that's what I've been doing for about the last week, being a plumber, which I'm not a good plumber. I'm a better electrician, I think, but I'm not a good electrician either, you know, so. But at least, I think now my wife at least gives me a C- in plumbing. It works now, and I was able to unclog the drain. Yay, you know. I had to buy 2 snakes because I broke one, and I had to buy this thing. I don't know if you've seen it. I was sitting there when I was working with a snake in the middle of the night, thinking this is terrible. I thought, if I could just cram my hose in here, it would blow the clog out, but you know, I knew that if you just stuck it in there and turned it on, it would squirt back in my face. So I need something to plug it up. Well, they make it. Have you guys seen this? Yeah, I went to Home Depot, I can't believe it. It's a little thing, looks like a hot dog. About this long, a little hole in it. When you turn the hose on, it inflates, jams itself in the pipe, and then it cleans it out. That was so cheap, $11. And it did work in conjunction with the snake. So yeah, if you get this clog, get you a snake, run it through, and then buy this little hot dog thing. Yeah, or come borrow mine. I don't need it again, right?
You just jinxed yourself again.
You what?
You just jinxed yourself again.
I did. In fact, it reminded me of my wife, because when I had that thought, I came in the kitchen and she said, "Hey, now that you've been working in the sink in the bathroom, can you clean the out and under the sink in our kitchen?" I said, "Yeah, I'll get to it." Well, when the pipe clogged, it made the one that goes into our disposal come off. It flooded everything under there. So, of course, now I cleaned out under the sink. I cleaned out because everything was soaked. And so yeah, I jinxed myself. Right, I'm gonna do that thing again.
sure your wife doesn't give you a hard time about being an engineer?
Oh, but no, not at all. No. Not that I fix everything. Don't ever have repairmen come in, but yeah, some things work and some don't. Yeah. I was feeling too confident because I replaced our thermostat the week before, and that worked fine. And, I mean, I don't tell her. I'm like, oh yeah, I replaced the thermostat. I know what it did. It was 4 wires in 5 minutes, and yeah. I do thermostat, honey. It's working great. I'm a genius. and then I was telling her, well, yeah, because when I met her, married her, she was a nurse. And I was like, yeah, you could have married a doctor, and the doctor would just pay for all this stuff, but at least you married an engineer, I can fix it, right? Since you make you have some, some consolation, but I don't think that helps. So yeah, well that's been my.
No, it's just about the doctor.
What's it?
Nothing.
Oh.
I married an engineer. That's all that needs to be said.
Well, I said I would never date one after me being one. I'm like, no, I'll date the nurses and the teachers. That's fine. Yeah. Yeah. Well, and I remember going up to D.C., going to Catholic University, because we had to walk across it to get to the cathedral. And I noticed they put the engineering school right by the nursing school. Well, they were probably planning. Thinking about it. Yeah. Well, let's see. But help if we had someone on the board, wouldn't it? That thing?
Except for 12 and 13.
That makes sense better too, doesn't it?
When we found out I was going into science,
You think I could have done that?
don't do engineering. Because they'll see this white wall and they'll say, isn't that beautiful?
So we'll just do the first two parts. The chi-square and the Marsculio procedure. Hope I said that right.
He predicted my life.
And since we're working with proportions, remember that's the categorical thing where 50% or 20% of people do this, or the good, bad, and the fair type of things where you got a ratio. And so we may have 2 or more characteristics. In fact, the example I do, I think I have 3 choices, so I did more than one. Let's see. So the example they're going to start out with is left hand versus gender. And so they got the dominant hand, left or right, are you male or female? So it's 2 categories, male or female, and left or right hand. And we got example, we got 300 people. So we're going to make it show, it usually shows up here too, right? Okay. So we set it up some fake data. We've got 300 set people, 120 girls, 180 guys, and then 12 of the girls and 24 of the guys were left-handed. So you want to ask yourself, is there a gender-based bias towards left-handedness? And so it's a proportion thing, right? We've got 12 out of 120, 24 out of 180. That's 10%. That's a little different than 10%. So you might be thinking, is there statistically, like we always want to argue it from a statistical point, not just, well, yeah, it looks like it, type thing. So we've got another test. So we've got the chi-square test. And it's like our other test, it's going to start out with, it's an inferential technique again. It's an analysis technique in our thing. And as usual, our null hypothesis is that there is no difference. The pi, remember, that's the proportion from the population. So that they're saying the proportion of left-handed girls is the same as proportion of left-handed guys. That's your null hypothesis, and your alternative is no. That's not. There is a difference. Okay, so here they're independent. Here they're not independent. Yeah. So we're going to come up with a test, just like we've always done. We're going to do some sort of calculate some statistic and compare it to the chi-squared statistic, and just if it's bigger, we reject the null hypothesis, or we could calculate that p-value. And if p was small, it means it's unlikely that these results are probabilistic, just random. Yeah. So here's your chi-squared, and just like usual, we're going to have a critical value, and if you fall out here, you reject it, or if your p is less than alpha, you reject it. And remember, you pick that. If you're 5%, 10%, like the same procedure we've been doing. Okay. So and it's got a set of degrees of freedom. And they don't mention that right away. So one of the things you're going to have to do, we're going to have to do like we always do, relate our proportion to what it should be, and then calculate this critical statistic like we've done with how far away from the mean is it, doing the z-test and those kind of things. And so the first thing they're going to calculate is what they call an average proportion. So they're going to take the whole total of people that have one of the characteristics, in this case the left-handedness, and figure out what is the average proportion. That would make sense, right? I mean, we got a population of people. We want to know what we think the average number of left-handedness is out of our sample. So hey, it's 12% based on the 12 from the women and 24 from the guys, and a total of 300. Okay, and then using this on the next slide, they're going to calculate what the expected percentage should be, thinking that you had 120 girls and 180 guys. So yeah, here what they do. Look. Oh, well, they're going to tell you what they're going to do first. Yeah, so to obtain the expected frequency, yeah, we're going to multiply this average proportion by the total number for the guys and the girls. And let's see, yeah, so down here, you would have expected that if the average percentage or the average proportion was 12%, that you would have had 14.4 left-handed girls and you'd had 21.6 left-handed guys. Just taking the average percentage times the total of girls and the average percentage times the total guys. Okay, so now I think, yeah, they did this table. It's nice. So here's your data. Here's what was observed. And notice, of course, that's redundant, right? You add that and that, you get that, add that, you get that. And here's what's expected. So now you've got a little bit, even plotting it or laying it out like this, you've got a clearer picture even of is there a difference? Well, you were a little under here and a little over here. So you could see how, but the data set, statistically, depending on what alpha you choose, you could conclude there isn't a difference. I forget how this one comes out, actually. I think it does come out keeping H0, I think. I can't remember. Okay, so our statistic that we're going to calculate to compare to the table, remember we've got in this case, our right skewed chi-squared distribution, and we're going to come out here, we're going to get a critical value, and then here's our statistic that we're going to calculate. It's a very simple statistic. We're just taking the observed minus the expected, the difference there, squaring it, normalizing it, if you will, to the expected value. And then summing them all up, and that's your error, if you will. It makes sense, right? Error in each little cell, really. I mean, to me, a lot of these techniques really make a lot of good sense. If nobody taught me this, I'd think, well, that's what I'll do. I'll kind of just figure out the normalized error and compare it to something. Now, to me, the leap of brilliance or whatever, and the part that we don't ever delve into is, where did the something come from? Where did the chi-squared that we compare it to come from? That's a lot of math that I think we would be ill-served, waste our time in here deriving that, because we're not statisticians. We're not going to try to come up with a new distribution, or we're not the guy working against us making up the student's t-distribution. I don't see the value in that. But if you're interested, yeah, grab one of those big statistics book and go at it, because they'll tell you. So here's this test statistic for each one. So the observed minus expected squared for each one. Sum them up. Well, there's our little number. Well, it's not very big. And so now we have to compare it to this critical value. And I think this is the example that they don't show you. They leave a little piece out. Yeah. They say our critical value, this was our test statistic, our critical value at the 0.05 level of significance is 3.841. And they say that's using 1 degree of freedom. They don't tell you how to calculate that until about 2 view graphs down. It's the number of rows minus 1 times the number of columns minus 1. So since we had a 2 by 2, we had 1 degree of freedom. And this comes straight out of the table. There's a table, or you could use the CHISQ inverse, right-tailed in Excel. I'll show you that in my example. But it's also table E6 in the back of the book, page 398. You can look it up. You can look up for alpha of 05 and 1 degree freedom, you'll get that. And so, yeah, so here you are. Here's your critical value. You reject if you're out here, you don't reject it here. We're way, you know, way down here. We're not even close to wanting to reject this null hypothesis. So you don't reject it, and remember how you properly state that. You don't say that, well, that proves that, you know, left-handed male and women are the same. You just say, well, we don't have enough evidence at this 5% level of confidence to kick it out. But then, always in my mind, then I turn around and say, well, yeah, that proves, you know, that left-handed men and women are the same proportion. but to state it correctly there. So again, nothing, I don't think anything out of the ordinary, nothing more than what we've done in the past. It's just a different test because, well, we had proportions. So we had this different distribution that we compare things to. Oh, well, here's a little twist. I mean, they showed you how to use that, calculate that average proportion and how to calculate the expected values. But again, a good test because I could see you having this kind of information all the time. All right? So now the natural extension would be, in this case, we only had two things, male versus female, right? Well, of course, you may have many more. So let's just extend it to where we had, you know, three populations, male, female, and animals or something, or, you know, we had 10 populations and that sort of thing. And so we're going to do the same thing. Our null hypothesis is going to be that they're all the same. There is no difference between them. There's no dependency on the group. And the alternative hypothesis is there is a difference. And remember, if you do conclude there's enough statistical evidence to reject this, you still haven't concluded which one was different. You know, if you had 10 of them, it may just be one of them different from the other 9, or they may all be different. So that's where this guy's procedure, this M2U00155 procedure comes in. And again, it's the same approach that we've done before, where you take, you know, you have all of the proportions, et cetera, and you compare them each to each other, and then compare the difference to another test statistic, not this one, but a different one that you calculate, and conclude if they're bigger than that, then okay, there's a difference. And so it's simple, the same approach we've done, again, just with proportions. All right, so we're using the same test statistic. Here's your degrees of freedom, and let's see, it's row minus column, row minus 1, column minus 1. Now in this case, they've got a 2-row example. Yeah. Why they went just with a 2-row? I mean, I guess, well, my example is 2-row too. I guess they're just setting themselves up for the future. You've got your average proportion, just like as before. You know, the number of people in each group or things in each group that have the characteristic, the total number of samples in each group. Decision rules the same. You've got a chi-square distribution with in case this is a 2 by 2 case, it would have been 1 degree freedom. In mine, I think in my example that I've got online that we'll look at, I've got 6 degrees of freedom. I think I had a 3 by 4, I think. We'll pull it up in a second and see. Well, let's see here. So let's see. So now, once you've got the null hypothesis and you've rejected it, now you want to compare between each one. So like I said, you're going to look at the proportions for each one, compare the difference between them to some calculated critical value. All right, and that critical value is going to look like that. Yeah. So you got your chi-squared number at your selected statistical level, each of the 2 different proportions, and the numbers in each one. Yeah, and this is a good note. Yeah, the pairwise, the critical range is different for each pairwise comparison. Yeah, and if the difference is bigger than this critical value, then you can conclude that, yeah, there was a difference between, you know, number 2 and number 5 or something, if you were comparing 2 and 5 or 2 and 3, or maybe they'll all be different. You know, again, all we know is when you reject the null hypothesis, at least one pair is different, and maybe all, but or some subset in between. Okay, so here's an example. Yeah. So let's see. We're thinking of switching to a trimester academic calendar from quarters, I guess. And so they took a random sample of 100 administrators, 50 students, and 50 faculty members to see if there's a difference, and they're going to look at the 1% level. So yeah, so favor, oppose, we've got administrators, students, faculty. So we've got 3 groups, two choices, either favor or oppose. Yeah, so we've got 200 people total. Yeah, all right. So first we want to get our average. So yeah, our null hypothesis is that they're all the same, that there's no difference between the opinions on the students, faculty, and administrators. Okay. And the way they've laid it out is the same way, well, I would use some colors, the way that, the same way they did before. This is the data up here, and then these are the expected values. And remember how you calculated the expected value. It was the total number of people that of things that had the characteristics. Our expected value would be, I'll see what we expected in favor. Yeah. Yeah, so let's see. Yeah, so they've taken, let's see, I think this is the one I worked. Let me pull it up for us. No, that wasn't the one I worked. Okay. Alrighty. Well, we'll wait. Okay, let's see. I'll work the next one. Okay. Alright, so they've taken the difference between the expected and the observed, squared it, divided by the expected, and come up with their statistic. And at the 1% level for the, let's see, it was 2 degrees of freedom, right? Because we had 2 rows and 3 columns. Yep. They've gotten this number, they compared it's bigger, they rejected.
Could you say the degrees of freedom again? How
It was row -1 times column -1. Yeah, so this should be 1% at 2. Let me make sure that I'm not lying to you. So you look at table E6. Okay, page 698. 1%. And I said 2 degrees of freedom, 9.210. Yep. Okay. Yeah. So yeah, and then it's funny that these they didn't say that in the on the view graphs. So yeah, and I did in my Excel, so you can remember row -1 times column, the number of rows. So again, this is had 2 rows, favor and opposed, 3 columns, administrators, students, faculty, so 2 degrees of freedom. Yeah,
Just the observed rows, right? Not the.
yeah, right, not the expected, right.
Yeah.
The rows in the data and the columns in the data set, yeah. That's funny, sometimes, funny little things like that. Yeah, it's like even, why didn't they make the expected row red for y'all? Just to make it stand out, just to help you. And then in my example, we'll see my example. I calculate this. The nice thing about this particular procedure is once you set up one table, you just copy it 2 or 3 times. I think I copied it 3 times, and then it's easy to calculate this, the expected, in the same table format, and then same with this statistic. I'll show you. It's really easy to calculate them all using the same table. It took about 5 minutes to work a problem like this once you set up the data table. And then, all right, so then to compare them, you're just going to compare each one to each other. So, compare group 1 to 2, 1 to 3, and 2 to 3. So this is the absolute difference between each of them. For example, comparing 1 to 2, 0.63 minus 0.4 is 0.23. Comparing 1 to 3, 0.11 in between, and 2 to 3, 0.34, right? And then you calculate that strange critical value that we had on the previous slide, that had the square root of the chi-squared number and the difference in the proportions and stuff. So notice that comment they made, there's a different critical range here for each comparison. Yeah, because there was a different P. Remember that here, when you do each comparison, there's that critical value here, right? So when I'm comparing 1 to 2, or 1 to 3, or 2 to 3, I'm obviously going to get something different under this square root each time. So this critical range is going to depend on which pair I'm comparing. And you see that's the case in here. Hey, I got my preview back. Yeah. Whatever I did, I fixed it up. So So now we compare this to the critical range. So since this is smaller than the critical range, there's no difference in 1 and 2. This is smaller than the critical range. There was no difference in 1 and 3. But this is larger than the critical range, so there's a difference between 2 and 3. So let's see, what was 2 and 3? That was students and faculty. Okay, so administrators and students were the same. Administrators and faculty were the same. The students and faculty were different. So again, this is kind of supporting what I'm saying. You know, you rejected the null hypothesis that they were all the same, but that's all you could say. You didn't know which ones were different, and so now you have to go each pair. Which again, I think if you didn't know what to do and you just were given a bunch of stuff, what would you do? That's exactly what you do. You come up with some test to prove they're different, and then look at each one. Or maybe, you know, if I didn't know what to do, I'd probably just look at each one. You know, I wouldn't do the test, the first test. I'd just say, let's look at each one, and if one was something different, you know, I'd just jump right to this if I didn't know what to do. And so again, your conclusion is at a 1% level of significance, there's evidence of the difference between the students and the faculty. That was that comparison here. Right, if we change that level of significance, right, we might come up with a different conclusion. So let's see. So here, let's extend the concept to where, okay, yeah, so they're building up slowly. They did 2 by 2 and then a 2 by 3. Now they're going to do R rows and C columns, a general one, okay? So again, your null hypothesis is the same. All the means, all the proportions are the same. They're independent. There's no difference. And then the alternative is there is some difference between at least one of them. Okay, same statistic, observed minus expected, squared over expected. And here's your degrees of freedom. Row minus 1 times column minus 1. I could have just said that on the last one when R was 2. Right? And you assume that you got at least some sort of frequency in your data, not that it's 0. You know, at least something is happening. You got some statistical information in here. And this is the same expected value expressed in a different way, right? Think about it. The row total divided by the n, or I say the column total divided by, so this is the total number of them, right? So if you divide the row total by, or the column total by n, that's it. Divide the column total by n. Think about back when we had the girls and the boys and the left-handed, right-handed. So we had it laid out, and it was logical to you then. We had it laid out. We had girls and boys, and we had left and right hand, and we said that we took the expected proportion was the total ratio times the number in each one. So the number, the number of girls would have been this column here, this number, and the expected would have been the total number of left hands, this total here divided by the n. And so if you did the row total divided by n times that, you got the expected proportion. Well, that's what this is, right? Row total times the column total divided by n. So it's calculated the same way. They're just expressing it different because I don't know why they're expressing it different. I guess
There's more than 2.
I guess, but you could have said the same thing before. Yeah, I guess just because there's more than 2. You're right. It makes it, but it's like I said, it's clear if you take the column total divided by n, that's the ratio of girls to total, and then that and then multiply by how many you had, or the left divided by total is the ratio of how many left-handers you had. It's the same approach, and the same conclusion. If your statistic is bigger than your chi-squared critical value, reject, otherwise don't. But again, you don't know which one. Yeah, and there's your degrees of freedom. So they restated what we're doing. So here's the example I've worked. So you've got meal plan versus your standing in the column. So your freshman, sophomore, junior, senior, and are you on the 20, 10, or no meal plan? And so let's see. So kind of looking at it. Is there a difference? Yeah, there's 76 different group and 70 on that. Doesn't look like there's a big difference, does it? It looks like, you got more freshmen than sophomore. Just kind of looking at it, it looks like the proportions are kind of the same. So let's see what happens when we work it out. Let's see which one am I on? So yeah, here's your H0. Oh yeah, okay. Yeah, the meal plan, class steady and independent, there's no relationship between them. H1 is there is. Now let's see, they throw out the answer and we'll look at my Excel. This is the last one we're gonna do. So let's see. They got the expected. Yeah, so here they're showing you how to calculate the expected row total times the column total over 200. So for example, this one here, row times column over 200, there's your expected. So now we can process each of those. So let's look at my Excel because it shows you easier how to do it. Let's see, there goes escape. 12 over 28. Oh, very large. And I tried to put everything in here to help you work it. Yeah. And let's see. Did I do anything else? Yeah, and then I should pull it down because we got some more calculations there on the bottom right now. Okay, so. All right. There's the picture. Okay, so it's pretty small. It's going down. Too small for you to read. Okay, so here's your original data, just laid out in Excel. So you can see what I was saying. So that's the F0, observed, expected. I just copied this table, threw it in there, and then did the column total times the row total divided by n. So it's very easy to use the same format. So here's each year expected. So I think they already had that. There's the 10.5 that we went over. And then the chi-squared statistic, remember, it's that minus that squared divided by that is for that cell. For this one, it's that minus that squared divided by that. So it was easy, again, to use the same table format and just, throw the formula in there. And then because I had the totals, if we're going to add them all up, the chi-squared final value of all of them summed up is going to be down here in the corner. So that's all I did. And I've thrown your formulas in there. Yeah, the first one is how to get the expected. That's this one here. And then the chi-squared thing is just the sum of all of them. So this is the guy. So like I said, this is the one for that difference. That's the one for that one's difference, each of them. So and notice this one, yeah, that one stood out to me. I looked at it. Wait a minute. Its observed value was 14 and its expected value was 14. So just an unusual one. But again, catch the things that look weird. So there's your chi-squared statistic, 0.709. And then either you can go to table E4, page 698 like we did, and our number of degrees of freedom was row minus 1, column minus 1. So we had 4 rows, 3 columns, so it's 6. You can go there, look it up. It's 12.592. Or you can use this chi-squared inverse right tail, since it's a right tail distribution, at 5%, because we picked 5%, remember? That's 6 degrees of freedom. And it'll come up with the same thing. And so, our idea was, do not reject it. So there's not enough evidence that class study and meal plan are dependent at this level of significance. So real, I think a very simple test, easy to use, be useful. I mean, to me, look here, you had, four rows, 3 columns. Once you got that example, you extend it to whatever, 20 rows and 100 columns if you need to. Easily make this decision. If there was a difference, so maybe just knowing that there's a difference is enough to conclude. Maybe there are sets of data from different days, and you just wonder, am I making different something about production? Is there something changed? You just know, oh yeah, there has. Maybe that's good enough. But again, it's relates to proportion. And if you want to find out if there was a difference, then you can do that procedure where we compare each one separately and decide which one's the bigger. So not bad, not a bad little approach. Seems like, I hope, and got an Excel to use. Now let's see. All right, so now that's good for that one. So now we switch gears and get out of the chi-squared and get out of these inferential tests and go to regression. And there's regression right there. Yeah, let me get it off. I've got that up in my face, I'll do that. And, well, okay. Okay, so. All right, so simple linear regression. So we want to learn how to use the Excel regression tool. And we want to do that so we can make a fit to our data, a model, whether it's y equal ax plus b, or y equal ax plus bx squared plus cx cubed plus other things. And then they talk about, in fact, a whole lot of these view graphs we could probably go through very quickly because they talk about real simple things like, what does the slope mean? What does the intercept mean? What's a line, what's not? As I think they're kind of assuming maybe you haven't approached it from that perspective before. And then they talk about prediction and interpolation. So they're trying to say, hey, once you got this line or this regression fit, you can now use it to estimate place, data that not where you have data. So between your data points, and then they make the case to not extend it outside the range of your data, which is probably not a bad idea. I mean, I know I've done that in the past, but in general, when you start extending these kind of regression fits outside the range of your data, weird things can happen, because it's not unusual if you do some sort of power fits and things to have, nice data coming along looking like this, and you fit some sort of power or polynomial to it, and it's pretty wacky outside the range. So in here you're doing okay interpolating, but boy, you move out here a little ways and you may get way out of bounds, and this isn't real. It was just an artifact of the fit. So when they say be careful to restrict yourself to within your data range or at least close by, or if you go out of your data range, think carefully about what you're predicting. That's how you get goofy conclusions, right? Okay, so we may use these scatter plots. You've done that, just you scatter plot x, y versus x, plot them out, and see what format the fit looks like. And then you'll have this correlation coefficient that's always spit out by Excel or spit out by my little old Hewlett Packard years ago. So we'll understand what that is. So it's going to measure the strength of the association. How good is your fit? And the closer it is to 1, the better. My example that I've got on the Excel, the first one I don't put any error in it. And so you'll see the correlation coefficient's 1. And that's good. It makes you feel good. And then I put error in it, and you can see how it's not 1. But it's still good. And remember, we always make this joke. Just because two things are correlated doesn't mean they cause each other. And I showed that the first day and we laughed at it. And we've had scatter plots and correlation for a while. All right, so we're going to do some regression analysis. And like I said, I'll go through these quickly because, hey, this is all stuff that as engineers you've seen a lot of this. Hey, you've got a dependent variable. That's the one we want to predict. That's y, independent x. But we may make combinations of these. So we may have, for example, my example, I have an x1 and an x2, and I'm predicting a y. And I also combine x1 and x2 as a product, or you could do a square, or other things. You could keep going. Just because it says linear doesn't mean we're only fitting lines. It's linear in your variables, yes, but I can make a variable that's a square or a product or something like that, and I'll show you how to do that. And this also extends much greater applications when we do design experiments. There's some interesting things you can do with the tables and having dummy variables and stuff that we don't need to get in here because our point here is just to fit some data. But in design experiments, we can go deeper into regression and how to make some pretty nice conclusions out of it, just depending on how you set up your data. So a simple linear regression is just x versus y. Yeah, so we're going to fit a line to it. And like I said, wow, we know these things. Not linear, linear, positive slope, negative slope. And the R squared relates to this, right? You got a nice strong correlation when they're all piled near the line, not so strong when they're not. And that's up to you almost in a judgment thing. You know, is that good? Well, it might be, depending on how you took your data and what this process represents. It might be horrible. You're going to have some thought on that. And see, I had a comment on that. Oh, the view graphs in a few do a real nice job of breaking up the error and showing you where the error comes from to help you understand what the R squared correlation coefficient is. Yeah, nothing between X and Y. Maybe that's what you wanted. And like I said, you're going to have Y equals an intercept plus a slope times X. That's the linear part. And then random error. And if you got no random error, then your R squared is going to be 1 on something that's a linear relationship. But you know, in general, if you're taking any kind of data from anything, well, of course you got error. And that's what the R squared is going to tell you, how far off you are. Let's see. Yes, what we got here. Data points, blue, red is your fit. Yeah, the random error is just, some observation out here, and it's off from the line for whatever reason. Experimental error, process error, real error, and the variation in your process, any of these kind of things. Yeah, there's your intercept, where it's the y-axis. My daughter's doing that. Yeah, there's your slopes. Well, I see a lot of these things were, stuff you had back in 3rd grade. Speaking of 3rd grade, you got any kids got the new math? My kids are too old. They're in their 20s now, except for Casey, who's 14, but she's been homeschooled now for 7 years. So I haven't seen the goofy new math. Have you seen this way to multiply, where you make a box, like you're going to do 12 times 24? Have you guys seen and you do a box?
Just kind of guess.
Have you guys seen this? None of you seen this. Have you seen it?
Say if you get close, it's
Yeah, there's two kinds of people. One that can say 2 plus 2 is 4, and one that says it's between 3 and 5. And the experts are the one that says between 3 and 5, and everybody claps. No, but you do this problem. Do this. 200, 40, 48, and then you add them all up. 288. Rather than doing it like we used to do. And there's even a worse way. I will show you that.
My daughter's in 1st grade. I got frustrated the other night because the directions were to write a number sentence. And I asked my wife, what the hell's a number sentence?
Yeah.
It's an equation. She
Yeah.
wanted to write.
But you had to write the
2
word.
plus 2 equals 4.
Yeah. My kids had to do my boys, when they went through 15, 20 years ago, they had this new math. It was called everyday math. That's what it was called. And rather than, how I felt like when I did math, you went through linearly. You learned how to add, and then you did 500 add problems. And then, you did single-digit numbers, then you did 2-digit and 1-digit, then you did 500 problems, etc. They did this smattering of crud. So you might learn to add today. Tomorrow you might learn to measure. The next day you might learn volume. Then you revisit adding, and then so it's like nothing was. It's like math is just this universe. Yeah, and they did a lot of those, and they would cry almost at the word problems because it'd take them forever to write out 2 plus. They had to use 2 plus 2 equals. Oh yeah, what is that?
I don't know.
I was shocked. I'd never seen that. I was like, gosh, I've done math. I've done multiplication all my life the standard way. What's the box? It was scary. But anyway, yes, we're back to doing lines like we did in 3rd grade. Still doing good lines. Yeah, so, it's going to give you an estimate, right, yeah. So, right, if you use since we obviously don't know what the error is, it's random and we don't know. Once you get your correlation fit for your intercept and your slope, you can predict now. That's the whole point of regression, right, is being able to predict. And then, so what least squares approach does, and what your regression in Excel does, is you've got a bunch of data points out here, and you're trying to shove a line through them. And which line do you shove through them? Well, it puts the line through them that minimizes all the sum of these square errors. That's why it's called least square, error. minimum square area. Which again, I think, if you didn't know what to do, and I said, fit a line through these points, you know, that's what you do with your eyeball. Let's fit the one that, you know, minimizes the distance between each of the points. And what's the distance? Yeah, it's the actual data point minus the prediction squared. Yeah, and so, okay, that's a good approach. Yeah, so let's see. Yeah, and what there's a comment in the box here, they've got a pile of formulas for what B0 and B1 are based on statistics, based all of them on the sums and the errors and stuff. There's a book, read them if you want, but yeah, we're going to use Excel. We're going to use Excel to give us B0 and B1. I mean, if you want to hand calculate them, that's fine. I don't believe I would ever do that. Yeah, so B0 is the intercept, B1 is the slope. You know what that is. I told you could go through this quickly, and we can go through these fairly quickly too. So they're wanting to relate house cost to square footage. Oh, good, yeah. So they've got a random sample of 10 houses, and so we know we can do that. We probably everybody probably done that anyway when you get ready to buy a house, right? So here's some prices, square footage. Yeah, these are nice houses, aren't they? Yeah. That's how I was looking at it. I was like, yeah.
Those aren't actual houses.
Yeah, here we got 24 square feet, 400,000. Yeah, exactly. But they're not beach houses. So here's the scatter plot. Like I said, you can do a scatter plot. And it does look like there's a linear correlation, you know, and that's you, you know, making a decision a lot of times with your own data. You know, it looks like we've got some goofiness going on in here. But that's okay. This is the one that had the fancy bathroom, right? And that was the one that left the garage off or something. You know how it is. So where's linear regression in Excel? I thought this was funny. It's one of the first times they've done this. You know, I always put it in your notes, but yeah, you know, it's under the data analysis again. It's called regression. Wow. You know, wouldn't have thought of that. And it pops up a menu like this, which you all have seen, and I tell you the direction. You know, and you pick a Y and an X. Click labels if you want to, so you got the titles.